What building materials and assembly strategies are best to design this healthy and resilient medical campus in Blantyre, Malawi? What is resilience? Environmental resilience utilizes the vernacular materials of the region to minimize the transportation and mass materials manufacturing. This form of resilience looks at the material's capabilities for being recyclable and reusable and explores production methods to determine if there are minimal amounts of toxic chemicals being emitted into the atmosphere. Economic resilience looks at how the material benefits the local community's circular economy. The material should provide work and steady income to locals during material production and building construction, and should be benefiting the community for years to come. Durability resilience refers to the physical strength and longevity of a material once it's assembled into a wall, floor, or roof. This type of resilience looks at the maintainability, structural strength, and upcycling potentials of each material. This resiliency definition helps to determine if the material can support the needs of a specific programmatic space and if the material can withstand natural disasters. Now that resilience has been defined, let's begin to determine what is needed to design and construct a resilient building or collection of buildings for the campus. The project needs materials that fit the local architectural language and has a low environmental impact in production, benefits the local economy as much as possible, and can withstand the tropical climate and will require little to no maintenance upon construction completion. In order to specify what materials can be best suited for the program, let's reiterate the primary programmatic elements for this potential building design. Laboratory spaces are the most constraining elements for this design. Lab spaces require airlocked rooms, surfaces that can be easily sterilized, and the structure of these spaces has to be able to hold a lot of weight for the necessary equipment. These spaces will need the most rigid and durable materials. Academic spaces can be expanded into multiple rooms or even multiple buildings to house the various support spaces for the lab. Elements such as classrooms, conference rooms, offices, and more will be housed in these areas. These programmatic elements do not need to be airlocked but do need to have a sufficient enclosure so that the interior spaces are protected from the natural elements. Flex spaces include the areas of the program that are completely exposed to the natural elements of the site. These elements may include pergolas, troughs, draining surfaces, and shaded seating areas. Because of the flexibility of these spaces, the material selections can also be more flexible and explorational.
Within the laboratory spaces, there will be a lot of equipment that needs to be supported by strong structural elements. This makes steel the ideal material for the structural frame. While steel is an imported material, it has high structural capabilities, which makes it a durable and reliable material choice for this space. Concrete is another imported material, presenting challenges around its high cost and unsustainable production methods. However, the laboratory space needs a material that can be easily sterilized and can be assembled into an enclosure that allows the air inside of the building to remain optimal for vaccine production conditions. Concrete is the best material for this enclosure of the laboratory space because it can support these needs. It has low maintenance requirements, it is extremely durable and strong, cheap to maintain, and would work great for floor slabs and wall slabs within these spaces. The academic spaces present more opportunities for material explorations. These spaces need to be structurally stable in order to create buildings that can withstand natural disasters and protect users from natural elements from the site. But other than that, the building itself can be flexible in terms of material choice. Gabion walls can be used to create buildings that have unique lighting characteristics within the interior of the building. The walls are made from a wire basket that is filled by local workers with stones from the site. The difficulty with using this material comes from the amount of labor that is required to create the walls, and because the durability of the enclosure depends on how well the stones are placed within the wire baskets. Looking at the Metropolitan Park south entrance, this project uses a steel frame as a structural system with gabion walls as the infill. These semi-permeable walls allow for air and light to filter through, creating optimal daylighting and passive cooling conditions within the space. For the academic spaces, rammed earth can be a sustainable solution to providing the building with unique visual characteristics. The layering of various soils comes from the color variations of different soils within the region. In this desert cultural center, concrete is used in conjunction with the rammed earth for structural stability, since rammed earth walls in this building are non-load bearing. Combining native soils with a small amount of cement, or even a natural binding agent known as lime, allows for the soil mixture to be bored into a mold and create this layering effect. Bricks are the local vernacular building material for this area. They are quick and cheap to produce and can be assembled in a variety of ways. Looking at the African Leadership University campus, this project utilizes brick as its primary building material. This building uses a variation in permeability and displays the various capabilities of brick. While bricks are versatile, they do have unsustainable production methods due to the use of firewood. Wood is being sourced from local forests, which feeds into the issue of deforestation. The good news is that there are alternatives to this drying method. Bricks can be sun-dried, or the wood from the trees can be substituted with bamboo or eucalyptus wood.
Flex spaces are the programmatic elements that invite the most material exploration and innovation to the design. Since these spaces do not have any structural requirements, there is room for the use of materials that are not suited for typical building construction. These materials include, but are not limited to, soil-stabilized bricks and recycled concrete. They can be used in a combination of ways to create flex spaces that promote water drainage during the storm seasons. Bamboo is one of the main materials that will be a perfect selection for flex space construction. This material can be used to create shaded seating areas as seen in the bamboo courtyard treehouse. The benefits of using this material is that it can be produced on-site. Bamboo is extremely cheap and fast-growing, making it an option for a construction material on MIB's site by the time this building is being built. This provides users with connections to nature through vegetation and promotes circulation paths for users by designing unique pathways to define the site. Each material that we have discussed has its benefits and pitfalls. Some materials fit best into specific programmatic spaces, making their specific needs for support outweigh the negative characteristics. These needs will be addressed in the next design phase. This material palette that is presented before you are some of the materials that will be explored for this project. Using combinations of these various materials will create a dynamic exterior condition that can help dictate programmatic spaces. So to recap, this program aims to promote vaccine production and trust in Malawi through training and education. This project acts as a manufacturing facility by providing flexible lab space, educational classrooms and meeting space, as well as outdoor space for community engagement. In order to achieve this, the design must aid in creating a healthy and successful future urban city in Malawi. To do this, environmental considerations and strategies such as energy production, ventilation, water management, vegetation, and food production are key. The various programmatic elements outlined each require unique conditions that can be met through the selection of resilient materials. Each material poses multiple solutions that best fit each programmatic space proposed.